All right. So thanks to both of you. And where we left off last week was that I made a grand claim. Well, I pointed out a couple of things. I pointed out through this fantastic halide video that actually running low-level kind of CUDA-kernel-y stuff fast is actually much harder than just running a bunch of for loops in order. And I showed you some stuff based on halide, which showed here's some ways that you can write it fast, and here's some ways you could do it quickly. And then I made the bold claim that being able to do this on the GPU through Swift is where we're heading. And so to find out how that's going to happen, let's hear it directly from Chris.
Sure. Thanks, Jeremy. So we will briefly talk about this. So we went through this video, and the author of halide gave a great talk about how in image processing kernels, there's actually a lot of different ways to get the computer to run this, and they all have very different performance characteristics, and it's really hard to take even a two-dimensional blur and make it go fast. But we're doing something even harder. We're not talking about two-dimensional images. We're talking about 5D matrices and tensors and lots of different operations that are composed together and hundreds or thousands of ops, and trying to make that all go fast is really, 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 really hard. So if you want to do that, what you do is you'd write a whole new compiler to do this, and it would take years and years of time. But fortunately, there's a great team at Google called the XLA team that has done all this for us. And so what XLA is it's exactly one of those things. It's something that takes in this graph of tensor operations. So think things like convolutions and matmoles and adds and things like that. It does low-level optimizations to allocate buffers, to take these different kernels and fuse them together. And then it generates really high-performance code that runs on things like CPUs, GPUs, or TPUs, which are crazy fast high-performance accelerators that Google has. And so XLA does all this stuff for us now, which is really exciting. And if you take the running bash norm example that we left off with and we were talking about, this is the graph that XLA will generate for you. And this is generated from Swift code, actually. And so you can see here what these darker boxes are is they're fusion nodes, where it's taken a whole bunch of different operations, pushed them together, gotten rid of memory transfers, pushed all the loops together. And the cool thing about this is all existing shipping technology that TensorFlow has now. There's a big question, though, and a big gotcha, which is this only works if you have graphs. And with TensorFlow 1, that was pretty straightforward because TensorFlow 1 was all about graphs. Jeremy talked about the shipping thingy. Ship. I don't know. My recursion's wrong. And so with TensorFlow 1, it was really natural. With TensorFlow 2, with PyTorch, there's a bigger problem, which is with eager mode, you don't have graphs. That's the whole point, is you want to have step at a time, you run one op at a time, and so you don't get the notion of these things. So what the entire world has figured out is that there's two basic approaches of getting graphs from eager mode. There's tracing, and there's different theories on tracing. There's staging, and taking code and turning it into a graph algorithmically. And PyTorch and TensorFlow both have similar but different approaches to both of these different things. The problem with these things is they all have really weird side effects, and they're very difficult to reason about. And so if Swift for TensorFlow is an airplane, we've taken off, and we're just coming off the runway, but we're still building all this stuff into Swift for TensorFlow as the plane is flying. And so we don't actually have this today. The team was working on the demo, and it just didn't come together today. But this is really cool. And so one of the problems with tracing, for example, is that in PyTorch or in TensorFlow Python, when you trace, if you have control flow in your model, it will unroll the entire control flow. And so if you have an RNN, for example, it will unroll the entire RNN and make one gigantic thing. And some control flow you want to ignore, some control flow you want to keep in the graph. And so having more control over that is something that we think is really important.
So Chris, this nearly there is as at end of April. This video will be out somewhere around mid to late June.
I
It'll
suspect
probably
it
be
will
up
be
and running
there.
by then.
Yes.
And if it's not, you will personally go to the house of the person watching the video and fix it for them.
So look, here's the deal. In 2-3 months, so that's July.
Okay.
Look on the Swift for TensorFlow main page. There should be a Colab demo showing this.
Okay.
So we'll see how the future, what the future.
And there should be a notebook in the Harebrained repo that will be called batch norm or something, and we'll have an XLA version of this running nice and fast.
And so Swift also has this thing called graph program extraction. And the basic idea here is that where Autograph and TorchScript are doing these things where they're kind of like Python, but kind of not. And Jeremy was talking before about how, like, you add a comment in the wrong place and TorchScript will fall over, and it's not. It kind of looks like Python, but really is not. With Swift, we have a compiled reasonable language, and so we could just use compiler techniques to form a graph, pull it out for you. And so a lot of things that are very magic and very weird are just very natural and plug into the system. So I'm very excited about where all this comes, but for right now, this doesn't exist. The airplane is being built. So one last thing that doesn't exist, because Jeremy wanted to talk about this, he's very excited, is there's this question about what is MLIR, and how does MLIR relate to XLA? What is all this stuff going on? What does this make sense for TensorFlow? And the way I look at this is that XLA is really good if you want high performance with these common operators like matrix multiplication, convolution, things like that. These operators can be combined in lots of different ways. Running batch norm is a great example of this. And so these are the primitives that a lot of deep learning is built out of. And XLA is really awesome for high performance, particularly weird accelerators. But there's a catch with this, because one of the things that power deep learning is the ability to innovate in many of these ways. And so depthwise convolutions came out, and suddenly with many fewer parameters, you can get really good accuracy wins. And you couldn't do that if you just had convolution.
Yeah, and like on the other hand, like depthwise convolutions are a specific case of grouped convolutions. And the reason we haven't been talking about grouped convolutions in class is that so far no one's really got them running quickly. And so there's this whole thing that like somebody wrote a paper about 3 years ago, which basically says, hey, here's a way to get all the benefit of convolutions but much, much faster. And we're still, the practical deep learning for coders course still doesn't teach them because they're still not practical because no one's got them running quickly yet.
And so we've been talking about this whole course. The goal with this whole platform is to make it an infinitely hackable platform. And so if it's infinitely hackable down to convolution, or give up all performance around a CPU, well, that's not good enough. And so what MLIR is about is there's multiple different aspects of the project, but I think the one Jeremy's most excited about is, what about custom ops? Right? How can we make it so you don't bottom out at matmul and convolution, and so you get that hackability to invent the next great convolution? Right? So the cool thing about this is that this is a solved problem. The problem is all the solutions are in these weird systems that don't talk to each other and they don't work well together, and they're solving different slices of it. So Halide, for example, is a really awesome system if you're looking for 2D image processing algorithms. Right? That doesn't really help us. Other people have built systems on top of Halide to try to adapt it and things like that. But this is really not a perfect solution. There's other solutions. So PlatML was recently acquired by Intel, and they have a lot of really cool compiler technology that is kind of in their little space. TVM is a really exciting project, also building on Halide, pulling together with its own secret sauce of different things.
And it's not just the compiler technology, it's also in each of these cases, they've built some kind of domain-specific language to make it easier for you, the data scientist, to write what you want in a quick and easy way.
Right, and so, and often, and what happens here is that each of these plug into the deep learning frameworks in different ways. Right, and so what you end up having to do is you end up in a mode of saying, TVM is really good for this set of stuff, and Tensor Comprehensions, which is another cool research project, is good at these kinds of things. And so I have to pick and choose the framework I want to use based on which one they happen to build into, which is not very
And again, we don't teach this in practical deep learning for coders because it's not practical yet.
Yeah.
You know, these things are generally research quality code. They generally don't integrate with things like PyTorch. They generally require lots of complex build steps.
The compile time is often really slow. They work really great on the algorithm in the paper, but they kind of fall apart on things that aren't, all those kinds of problems. So our goal and our vision here with TensorFlow, but with Swift for TensorFlow also, is to make it so that you can express things at the highest level of abstraction you can. So if you have a batch norm layer, totally go for that batch norm layer if that's what you want, use it and you're good. If you want to implement your own running batch norm, you can do that in terms of matmuls and adds and things like that, fine. If you want to sink down farther, you can go down to one of these systems. If you want to go down farther, you can write assembly code for your accelerator if that's the thing you're into. But you should be able to get all the way down and pick that level of abstraction that allows you to do what you want to do. And so I just want to give Tensor Comprehensions as one random example of how cool this can be. So this is taken straight out of their paper. This is not integrated. But Tensor Comprehensions gives you what is basically like Einstein notation on total steroids. It's like einsum. Yes, good point. It's like einsum, and but taken to a crazy extreme level. And what Tensor Comprehensions is doing is you write this very simple code. It's admittedly kind of weird, and it has magic, and the syntax isn't the important thing, but you write pretty simple code, and then it does all this really hardcore compiler stuff. So it starts out with your code, it then fuses the different loops, because these two things expand out to loops. It does inference on what are the ranges for all the loops and what the variables that you're indexing into the arrays do. Then fuse and tile these things, fuse, tile, then sync the code to like make it so the inner loops can be vectorized.
This is actually a particularly interesting example because this thing here, GEM, is a generalized matrix product. This is actually like the thing on which large amounts of deep learning and linear algebra and stuff is based on. So like a lot of the stuff we write ends up calling a GEM. And the fact that you can write this thing in 2 lines of code, if you like look inside like most linear algebra libraries, there will be hundreds or thousands of lines of code to implement something like this. So the fact that you can do this so concisely is super cool. And so the idea that then we could do like, you know, nice little tweaks on convolutions or whatever in similar amounts of code is something that I get very excited about.
Yeah, me too. And the other thing to consider with this is that, again, generating really good code for this is hard. But once you make it so that you separate out the code that gets compiled from the algorithms that get applied to it, now you can do search over those algorithms. Now you can apply machine learning to the compiler itself. And now you can do some really cool things that open up new doors.
So, I mean, that's actually really interesting because in the world of databases, which is a lot more mature than the world of deep learning, this is how it works, right? You have a DSL, normally called SQL, where you express what you want, not how to get there. And then there's a thing called a query analyzer or query compiler or query optimizer that figures out the best way to get there, and it'll do crazy stuff like genetic algorithms and all kinds of heuristics. And so like what we're seeing here is we'll be able to do that for deep learning. Yep. You know, our own DSLs and our own optimizers, not deep learning optimizers, but more like database optimizers.
Yeah, so it's going to be really exciting. So we're building all this. The MLR part of this is longer time horizon. This is not going to be done by the time this video comes out. But this is all stuff that's getting built, and it's all open source, and it's super exciting. So to overall summarize all this TensorFlow infrastructure stuff, so TensorFlow is deeply investing in the fundamental parts of the system. This includes the compiler stuff, also the runtime, op dispatch, the kernels themselves. There's tons and tons and tons of stuff, and it's all super exciting. So let's stop talking about the future.
Yeah, I mean,
that's kind of boring. Like, what can we do today?
Yeah, this is very exciting, Chris, that, you know, sometime in the next year or two, there'll be these really fast things. But I actually know about some really fast languages right now.
Really?
Yeah, they're called C, C++, and
seriously?
Swift.
Oh.
Yeah, let me show you what I mean.
Oh, okay.
These are actually languages that we can make run really fast right now. And it's quite amazing, actually, how easy we can make this. Like, when you say to an average data scientist, hey, you can now integrate C libraries, the response is not likely to be, oh, awesome, right? Because like data scientists don't generally work at the level of C libraries. But data scientists, work in some domain, right? You work in neuroradiology, image acquisition, or you work in astrophysics or whatever. And in your domain, there will be many C libraries that do the exact thing that you want to do at great speed, right? And currently, you can only access the ones that have been wrapped in Python, and you can only access the bits that have been wrapped in Python. What if you could actually access the entire world of software that's been written in C, which is what most software has been written in, and it's easy enough that, you know, an average data scientist can do it. So here's what it looks like, right? Let's say we want to do audio processing, okay? And so for audio processing, I'm thinking like, oh, how do I start doing audio processing? And in my quick look around, I couldn't see much in Swift that works on Linux for audio processing.
So you write an MP3 decoder from scratch, right?
Yeah, I thought about doing an MP3 decoder from scratch, but then
lots of signal processing.
I figured like, people have MP3 decoders already. What are they doing? And I looked it up on the internet, and it turns out there's lots of C libraries that do it.
Yep.
And one popular one, apparently, is called SOX. Right? And I'm a data scientist, I'm not an audio processing person, so this is my process last week, was like C, library, MP3, decode, and it says use SOX. So look at this. I've got something here that says import SOX. And then it says init SOX, and then it says read SOX audio. Where did this come from? Well, this comes from a library. Here it is, SoundExchange. This is what C library homepages tend to look like. They tend to be very 90s. And basically, I looked at the documentation, and C library documentation tends to be less than obvious to kind of see what's going on, but you know, you just kind of have to learn to read it, just like you learn to read Python documentation. And so basically it says you have to use this header, and then these are the various functions you can call. There's something called init, and there's something called open. So here's what I did. I jumped into Vim, and I created a directory, and I called it Swift SOX. And in that directory, I created a few things. I created a file called package.swift. And this is the thing that defines a Swift package. A Swift package is something that you can import. And you can actually type Swift package in it, and it'll kind of create the skeleton for you. Personally, my approach to wrapping a new C library is to always copy an existing C library folder that I've created and then just change the name. Because every one of them has the same 3 files, right? So this is file number 1, you have to give it a name, and then you have to say what's the name of the library in C. And in SOX, the name of the library is SOX. Step 2 is you have to create a file called sources SOX module.modulemap. And it contains always these exact lines of code, again, where you just change the word SOX and the word SOX and the word SOX. So it's not rocket science.
So what this is doing is this is saying that you want to call it SOX in Swift. They called it SOXU.h for some reason.
Well, I actually called it SOXU.h,
okay,
which we'll see in a moment.
And then, but the library isn't, it gets linked in by libsox.
Yeah, exactly.
So all these things in C can be different?
Yeah. So, you know, most of the time we can make them look the same.
Yep.
And so then the final third file that you have to create is the .h file. And so you put that in sources, SOX, and I call it SOX umbrella header.h. And that contains one line of code, which is the header file, which, as you saw from the documentation, you just copy and paste it from there. So once you add these 3 files, you can then do that. Okay, and so now I can import SOX, and now this thing, this C function, is available to Swift, right? And so this is kind of wild, right? Because suddenly, like, a lot of what this Impractical Deep Learning for Coders course is about is like opening doors that weren't available to us as data scientists before, and thinking, what happens if you go through that door, right? So what happens if you go through the door where suddenly all of the world's C libraries are available to you? What can you do in your domain that nobody was doing before, because there wasn't any Python libraries like that? So and so what I tend to do is write little Swift functions that wrap the C functions to make them look nice. So here's init SOX, which checks for the value I'm told the docs say to check for, and SOX open read. For some reason you have to pass nil, 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 so I just wrapped that. And so now I can say read SOX audio. And so that's going to return some kind of structure. And so you have to read the documentation to find out what it is, or copy and paste somebody else's code. Very often, the thing that's returned to you is going to be a C pointer, and that's no problem. Swift is perfectly happy with pointers. You just say pointee to grab the thing that it's pointing at, and according to the documentation, there's going to be something called signal, which is going to contain things like sample rate, precision, channels, and length. And so I can, let's run those 2. So I can run that, and I can see I've opened an audio file with a C library without any extra stuff.
And so one of the things you can do is you can type SOX tab, and it Now here's all the stuff that's coming in from that header file.
That's wild. Yeah, super cool. So, so now I can go ahead and read that, and this is kind of somewhat similar to Python. In Python, you can open C libraries in theory and work with them, but I don't do it because, almost never do it, because I find that when I try to, the thing you get back are these C structures and pointers, which I can't work with in Python in a convenient way. Or if I do use things like PyBind11, which is something that helps with that, then I have to create all these make scripts and compile processes, and I just don't bother, right? None of us bother. But in Swift, it's totally fine. And then the nice thing is we can bring Python and C and Swift together by typing import Python.
The unholy marriage.
Yeah, now we can just say, we can take our C array and say make NumPy array and plot it, right? So we're really bringing it all together now. And we can even use the ipython.display, and we can hear some audio.
Hi everyone, I'm Chris.
Hi everyone. Hi Chris.
Hi Jeremy. Thank you, Jeremy.
My pleasure. All right, so
why did I say yes to this again?
okay, so this is pretty great, right? We've got Swift libraries, C libraries, Python libraries. We can bring them all together. We can do stuff that our peers aren't doing yet. But what I want to know, Chris, is how the hell is this even possible?